Buenas tardes, soy Dr. Simon Nicholas Kemp de la Universidad de Guadalajara. En el marco de la Feria Internacional del Libro y el 7º Coloquio de Astronomía, Universo y Sociedad, presentamos la conferencia de nuestro invitado distinguido, Dr. Sun Kwok. Dr. Sun Kwok es un astrónomo profesional especializado en astroquímica y evolución estelar. Es mejor conocido para sus estudios sobre las nebulosas planetarias y las muertes de estrellas como el Sol, área en la que también hemos tenido unos astrónomos activos en la Universidad de Guadalajara. Recientemente, el Dr. Kwok ha estudiado sobre la formación de compuestos orgánicos complejos en las etapas tardías de evolución estelar. Es autor de muchos libros, incluyendo Origen y evolución de nebulosas planetarias, Mariposas cósmicas, Cosmic Butterflies, Polvo de estrellas, las semillas cósmicas de la vida, que es el tema de la plática hoy, y Nuestro lugar en el universo, de lo que acaban de publicar, volumen 2, hace unas semanas, con subtítulo El acercamiento científico a descubrimiento. Él ha sido observador huésped en el telescopio espacial Hubble y el observatorio espacial infrarrojo. El Dr. Kwok ha hecho servicio extensivo en organizaciones internacionales, ha sido presidente de 2 comisiones de la Unión Internacional Astronómica, famoso IAU, Astrobiología y Materia Interestelar, chairman del Grupo de Nebulosas Planetarias. Sus afiliaciones académicas incluyen Dean, que es como rector de ciencia, y profesor de ciencias espaciales y director de investigación especial en la Universidad de Hong Kong. Director del Instituto de Astronomía y Astrofísica en Taiwán, profesor de Astronomía en la Universidad de Calgary en Canadá y actualmente trabaja en la Universidad de British Columbia en Vancouver, Canadá. Hoy invitamos a Dr. Kwok a dar una plática sobre sus trabajos recientes en la formación de compuestos orgánicos complejos y origen de la vida, polvo de estrellas, las semillas cósmicas de la vida, o como la plática va a estar en inglés, Stardust, the cosmic seeds of life.
Wow, thank you very much, Simon. I'm happy to give this talk in Mexico.
Thank you very much. Please carry on.
Hello. Today I'm going to talk about a question which has been asked by humans for thousands of years. And the question is, where do we come from? Now, it is among all cultures, there is the old ancient belief that of divine intervention. That means that we are created by a god or gods, and we owe our existence from a supernatural being. A modern variation of this idea is extraterrestrial experimentation. So there may be intelligent aliens who put us there or created us of some basic ingredients. The alternative is the concept of panspermia. Now, it has been suggested that life on Earth came from somewhere else, that through interstellar travel, seeds are planted on Earth by life elsewhere. But of course, this problem does not solve the problem of origin of life. It only shifts the problem to somewhere else. Now, for hundreds of years, there was also a popular belief that life can come out of the non-living. An example is cited by the fact there are worms coming out from decaying meat and so on. Now, it was not until the experiment by Louis Pasteur in 1850 that he demonstrated quite convincingly that life can only come from the living, and all the microorganisms that coming out from gravy or whatever just because of contamination by microorganisms in the air. So today on Earth, life can only come from life. Now, after the experiment of Pasteur, then it was scientists came to understand that living organisms are made up of molecules, in particular organic molecules. And this organic matter is different from, say, minerals or rock and so on. It possesses something which called vitality. And this vitality is what separates the living from the non-living. Now, however, in the late 19th century, in the laboratory, chemists were able to artificially synthesize various kinds of organic compounds from inorganic matter. So that led to the demise of the concept of vitality, and we no longer believe there is something fundamentally different between organic molecules and inorganic molecules, because organic molecules can be made in the laboratory from inorganic matter. Now, in the 20th century, that it was proposed that the life on Earth could have been made through a chemical process based on physical and chemical processes, that life was created a long time ago. Now, the difference is that of the time scale, because the Earth is billions of years old, and the condition at that time could be quite different from the conditions that we have now. And in 1953, there was a famous experiment by so-called Miller-Urey experiment, where the molecules methane, ammonia, water, plus hydrogen were put into a chemical contained, and being some energy injected into it, for example, through electrical discharge. And then after a few days, it was found that organic molecules like amino acids, sugars, and so on can be found as deposits of this experiment. So this gave the idea of the chemical origin of life a great boost, because it was thought that during the early days of the Earth, in some so-called favorable environment, that life could originate from just simple chemical reactions. So this paradigm was popular for over 50 years. Now today I'm going to talk to you about a new possibility, and this is that we on Earth drew upon raw materials, namely organic compounds, from stars, and after they were delivered to Earth, then life on Earth developed out of these stellar materials. Now, the new evidence that we have now, contrast to, say, a couple of decades ago, is that we now know that complex organic compounds are not just the sole domain of the Earth, but in fact, they can be found everywhere in the universe. And so this is the theme of my talk, about the widespread presence of organics, and in particular, how organic matter are routinely being made by stars. Now, as for the delivery, we also understand for the last 50 or 60 years that the Earth is not a closed system. So the Earth, Moon, Mercury, and Mars all have been subject to by events of external bombardment, and we can see evidence on the Moon that there are craters that are the remnants of external bombardment. Also on Mars and also on Mercury, there is evidence of so-called impact craters. Now, the Earth being a larger body than Mars and Venus, and Mercury, that we must have also suffered from similar impacts from the past. But the difference of the Earth is that the Earth has a very active geological history. So a lot of these remnants were wiped out by geological processes. But nevertheless, we can see, for example, in this crater in Arizona, that is definitely an impact crater due to an impact of an asteroid about kilometers long. And these events actually can happen on regular time scales. Now, this is a picture of the crater on Earth. Now we know that there are probably tens of thousands of craters on Earth, but because of geological activities, only hundreds can be still visible today. So what did these external bombardments bring to Earth? There are some simple things that are necessary. For example, our ocean. The water in the ocean probably brought in by comets, and there are carbon dioxide in the atmosphere, and they dissolved into water, forming carbonate in our Earth's crust. So since the Earth and the planetary solar system was formed from a pre-solar nebula, which represents an accumulation of material ejected from previous generation of stars, therefore the Earth must have inherited chemical elements made by stars. Now, since the 1950s, we know that we owe a lot to the stars because our human body has a lot of biomolecules, and these molecules are based on atoms such as oxygen, carbon, nitrogen, calcium, phosphorus, sulfur, as well as some not so common elements like iodine, iron, magnesium, manganese, and so on. So all these chemical elements are necessary for life, and all these elements, chemical elements, they originated from stars. So actually, there is a very strong star-human connection based on the presence of chemical elements that we have in our body and on Earth. Now, in the 1950s, it was realized that stars are very productive nuclear plants. The sun, for example, convert hydrogen into helium by nuclear reaction, and then red giant stars, they convert helium into carbon, and also all the heavy elements that we have are all the result of nuclear reactions inside the core of very old red giants, and these elements are brought up to the surface of red giant stars through the process of convection. So in the case of our Earth, our sun, in 5 billion years, the sun will become a red giant, expanding to 100 times its present size. It will fill a large part of the sky, and it also be hundreds times more luminous. So this red giant star, the future of the sun, will evolve further to be even more luminous and larger, and they also, in the process, develop a very strong stellar wind. So by observing similar stars in our own galaxy, we know that these typical stellar winds from red giant stars can be ejected materials at a rate of 600 trillion tons per second. And that's a very strong stellar wind. Now, what are in these stellar winds? Now, in the last few decades, we have at our disposal modern astronomical instruments, for example, millimeter wave telescopes that can detect radio waves at frequencies as high as tens or hundreds of gigahertz. Now, at those frequencies, we are able to detect the presence of molecules. For example, the simple molecule carbon monoxide, the the most basic transition is a frequency of 115 gigahertz, and that was discovered in 1970. So we detect molecules by a number of ways. So either they can be rotating, and that they will emit microwave or millimeter wave radiation. Either the atoms in the molecules could be stretching, or they could be bending. In this way, they emit infrared radiation. So now with these modern millimeter wave telescopes, we have detected all kinds of organic molecules in space. So we have simple hydrocarbons like methane, acetylene, we have alcohol, and aldehydes, and all basically almost every class of organic molecule that we know in the laboratory have been detected in space. Now people ask, well, the stars are very far away. How can you be so sure that you are detecting these molecules? But actually, the detections are very precise, because we have detectors which can be tuned to frequencies as accurate in one part in 10 million. So since molecules all have specific signatures at different frequencies, so there is no doubt that we are detecting the molecules that we say we are. Now, however, this wasn't that popular in the 1960s. Astronomers at that time thought that it is impossible to have molecules in space, because molecules are very easy to be dissociated by interstellar ultraviolet radiation, and also the density in space is so low, they think it's very difficult to make a molecule out of atoms, because collisions among atoms are so rare. But now we know this is not true, because we have over 200 molecules detected in space, or even a prominent scientist could be wrong. Now, going back to the case of red giant stars, okay? So in the stellar winds of red giant stars, we have detected over 80 molecules. So using these techniques of either rotational transitions or vibrational transitions of these molecules. And they have simple, like chain molecule, for example, cyanopolyion, HCN, HC3N, HC5N, and also rings like C2H2, and so on. Now, not only these stellar winds or red giant stars make molecules, they also make solids. So by the development of infrared astronomy, we can detect the presence of solids by the infrared radiation they give out. So by comparing the signatures of the signal, infrared signal, to the laboratory measurements that we have on Earth, we can tell what kind of solid we are detecting. So the most common kind are minerals. So for example, silicates, which is like sand on our beach, is very common. So this is the infrared signature of amorphous silicates, and you can see that the signature is very prominent, that they have been detected in thousands of red giant stars by infrared observations. Now, how do they form? Now, well, actually, we don't really know how do they form, because the density in the stellar wind is very low, but we know that they form very quickly. As a matter of fact, they can form on time scales of days, and somehow the oxygen, silicon, aluminum atoms in the stellar wind, they condense to form solids like silicates. Now, beyond silicates, there are all kinds of other minerals, even like similar to ruby and sapphires, various kinds of gems that we have on Earth. Now, following the red giant stage is the stage we call planetary nebula. So, for example, the Sun will become a planetary nebula after this red giant stage, then these planetary nebulae are very spectacular because they were light up by atomic emission from at that time a very hot central stars. And they are extremely interesting objects to study, not only because of their beautiful morphologies and appearances, but because what they contain. So they have, like I said earlier, contain various different kinds of atoms, molecules, and solids. Now, however, in the 1970s, through accidental discovery of an infrared telescope on the Kuiper Airborne Observatory, which is based on a C-140 transport aircraft, that there were some mysterious signals discovered. These infrared signatures are not something that astronomers were familiar with. So this family of infrared signatures at 3.3, 6.2, 7.7, 8.6, and 11.3 microns have never been seen by astronomers. Now, however, it was soon realized by comparing the infrared signatures of organic molecules that they are coming from organic compounds. So as I mentioned before, when the atoms in a molecule, they begin to stretch, or when they bend, they emit infrared light by making comparison to the infrared light emitted by laboratory molecules and these astronomical signals. We can tell what the molecules are, and these are what we call aromatic molecules. These are ring-like molecules, which, like benzene and other things that make up the many of the biomolecules that in our body. Now, then astronomers want to ask, where do they come from? Where do these complex organics come from? Now, because we know that they were not present during the red giant stage, they only appear during the planetary nebula stage. So I was really curious on what is the earliest appearance or evidence of synthesis of these organic molecules. And that had to be during a transitional phase between red giants and planetary nebula. Now, but this is a missing link which were not known before. And fortunately, in the 1990s, Bruce Rifneck and I were able to discover about 30 what we call protoplanetary nebulae, and these are transition objects between red giants and planetary nebulae. So I appear an example of a protoplanetary nebulae called the Cotton Candy Nebula that we took a picture using the Hubble Space Telescope, and that is one of the protoplanetary nebulae that we discovered. Now, after we discover all these 5 protoplanetary nebulae are discovered by us, and those are all new kinds of objects. After the discovery, we're able to follow up observations with them in, for example, in the infrared, and we were able to detect not only the 3.3 micron emission feature, which are due to aromatic molecules, we also detect a feature at 3.4 micron, which is a signature of aliphatic organics. Now, what's aliphatics? Aliphatics are a simple, similar to fat and oil in our body, and they are chain-like instead of ring-like, and they have specific signatures which are different from aromatic molecules. So this is a spectrum where we took with the Keck telescope. So in addition to the of a planetary nebula, IRS 21282 plus 5050, and is in addition to the aromatic signature, we also see signatures of aliphatic compounds. So now these signatures, these organic compounds are not only seen in planetary nebulae, they are also actually seen in many nice nebulae in our own galaxy, as well in the external galaxy. So this is the spectrum of the galaxy M82, and you can see that it has a very prominent feature similar to what I showed earlier from planetary nebulae. So galaxies. As a matter of fact, galaxies as early as 10 billion years ago already have evidence for organics in them. Now, what is the chemical structure of these organics? Now, again, we have to turn to our knowledge of organic chemistry on Earth. And the most common organic on Earth is something called kerogen, which is a remnant of living bodies millions of years ago, and they are buried in the surface of the Earth, and they are the precursors of oil and natural gas. Now, if you look at the chemical structure of kerogen, it has a mixture of rings, which are dark color and connected in some kind of random manner by aliphatic chains. Now, so as I mentioned before, kerogen is by far the most common complex organics on Earth, and they represent the major reservoir of carbon on Earth. Now, the question is, do we have evidence of this kind of complex organic matter outside of the Earth? So we are suggesting that the infrared signatures that we are seeing in planetary nebulae and also in external galaxies have a chemical structure of this kind, which we call MON, which stands for mixed aromatic aliphatic organic nanoparticles. And they have not only carbon and hydrogen, they also have mixed in various other elements like oxygen, nitrogen, and sulfur, and they have very complex and unorganized structure. So there's similar this kind of organics also in our solar system. And it turns out, yes. Now, we know that there are lots of solids in our solar system. We have asteroids and comets, and they sometimes fall into the Earth's atmosphere in the form of meteors. And if we look on the surface of the Earth, these meteors sometimes leave a piece of remnant, which are meteoroids. Now, the good thing about meteoroids is that we can pick them up when we can actually analyze them in the lab. So for some kind of meteoroid, could be called carbonaceous chondrites, they contain a huge amount of organics. Now we can actually, meteorites come in various sizes, actually are very easy to see for example, in Antarctica, because we have a snow white background, and these micrometeoroids, they are black or colored, they are easy to pick up. So now, in the 1970s, chemists are beginning to analyze these meteorites and found them to have all kinds of organics in them. Now, first, people were skeptical because they said, oh, maybe your experiment were contaminated by organics on Earth. But actually, after repeated experiments, we now know that the meteorites contains all kinds of organics. Actually, every organic compound that we know on Earth are also present in meteorites. Now, not only we have all our common organic compounds, we actually have more. They actually have more. For example, in our body, we only use 20 amino acids, but over 100 different kinds of amino acids are found in meteorites. So it is quite clear that the organics that we have in the meteorites are not the result of some kind of contamination, but they were actually made or synthesized outside of the Earth. So now we also have evidence that because on Earth, all the amino acids are left-handed, whereas in the amino acids in the meteorites, they have a mixture of right and left-handed. So again, this evidence that they are not contamination of Earth. So what do these organics look like? Now, in addition to molecules, they are also organic solids. Now, these solids, which is called insoluble organic matter, or IOM, they have a mixochromatic aliphatic structure, and they have also heavy elements like oxygen, sulfur, and nitrogen, and so on. So from studying of these meteorites, we know quite sure that in space we can make complex organics without the presence of life. Now, just going back to remind everyone that the complex organics on Earth, like kerosene and oil and coal and so on, are all the result of life. Now, we also have been studying comets. Now, astronomers used to think that comets, there is no boss, but in fact, recent space missions like the Rosetta mission have detected a lot of complex organics from meteorites. We can also fly an airplane to the upper atmosphere and collect interplanetary dust, and they also found to have signatures of complex organics similar to the kind of infrared signatures that we see in planetary nebulae. So the Saturn's moon Titan has lots of organics. Its surface are filled with lakes and sand dunes, which are made of organics. As a matter of fact, it is estimated the total amount of hydrocarbons on Titan is larger than the oil and gas reserve on Earth. So there is a lot of complex organics on Titan. Now, in the outer solar system, for example, in Pluto, that is, for example, the recent flyby by the New Horizons spacecraft, they found they take pictures of the surface of Pluto, and the astronomers have analyzed the colors of the surface of Pluto and came to the conclusion that Pluto is also covered by complex organics. So we know that complex organics are building blocks of life. We have a middle axis for proteins. We need phosphates for nucleic acids, and so on, sugar for nucleic acids, and so on. Now, the important thing, or unexpected discovery, is that all the basic ingredients of life are now found in space, and we know that they can be made abiologically. So that means we don't need life to make these complex organics. So now, in the past, people thought the solar system and the planets and Earth are the result of a mixture of basically various kinds of chemical elements. But now we know that it's probably more complicated than that. So we know that in planetary satellites like Titan, in comets, in the planetary dust particles, in meteoroids, there are lots of complex organics in there. So the Earth, early Earth, quite possibly have been reached by the presence of all these extraterrestrial organics. Now, another step further is that where did these organics come from? Now, we have already established there are lots of complex organics in the solar system. And we have also independently discovered that stars and planetary nebulae can make very complex organics. So is there a connection? Is it possible that stars are making all kinds of complex organics? They were ejected into interstellar space. They were collected into nebulae, out of which the solar system was formed. Now, this is actually quite a drastic hypothesis, because many astronomers still hold on to believe that the universe is simple. So we have stars and galaxies, which are nothing more than just simple atoms, whereas the solar system is complex and dirty, and is not easy to convince other people that the stars and galaxies are also quite complex, and they may also have complex organics like we have in the solar system. So the evidence that we have now is that we have complex organics in the solar system, and they are in stars, they are in the stellar clouds, and they are in galaxies and in galaxies as old as 10 billion years. So we have a picture or a cartoon like this. So we have old stars, which like the sun will, which is a very typical star, which eventually become a planetary nebula. So out of this planetary nebulae, they eject complex organics. These complex organics are ejected into the diffused interstellar medium. Through gravitation, they condense into clouds, out of which new stars and new planetary systems are formed. Now, after they are formed, for example, this is the Earth, then in the solar system, we have comets, we have asteroids, we have interplanetary particles, and they, from time to time, they hit the Earth. And they, through this process, they enrich the Earth with complex organics. So the hypothesis that I'm putting forward to you is that stars are capable of making very complex organics. And the availability of these complex organics in the primordial solar system may have contaminated the Earth, early Earth, with complex organics. So the origin of life should have been a lot easier because of the presence of all these ingredients. So I want to summarize with a few simple messages. I hope I convinced you that old stars like red giants and planetary nebulae, they are capable of synthesizing very complex organics, well, in addition to atoms and molecules and minerals. They also eject these compounds through the process of stellar winds into the interstellar space and spread all these compounds throughout the Milky Way galaxies. So since these organics are in the interstellar cloud, they may congregate themselves into a pre-solar nebula, out of which our sun was formed and our planetary system was formed. So the complex organics inherent in this stardust may have contributed to the origin of life on Earth. And that is my message to you today. Now, for you who are technically oriented, I put in here a few references that you can see in more details the evidence that we have on the complex organics in stardust. Now, I also have a book, popular book, called Stardust, to compare the cosmic seeds of life. It has 22 chapters. It covers a wide range of topics, only a very small fraction I'm able to talk about today. So I hope I interest you to learn further about this very exciting subject of where we come from, whether we do have a connection of our existence to stars, and this book contains a lot of, I think, thought-provoking ideas that you may find interesting. Thank you very much, and thank you for your attention. And if you have any questions, I'm very happy to answer them.
Okay, Professor Kwok, thank you very much for your talk. It was very interesting. Now we have about 10 minutes or so in which we can ask you some questions. Your talk concentrated mostly on the possibility of how life formed on Earth, but you say all these complex molecules are everywhere in the universe now. So in this, I think a natural question is, what do you think about life on other planets? Do you think it's it's everywhere, or what do you think?
Yeah, we are living in a very exciting times. I mean, not only we have the astronomical capabilities to detect complex organic compounds in space, we also have various space missions going to solar system objects. You know, like we probably will be heavily engaged in looking for life on Mars and maybe on Titan. So I think it is very exciting times. And as the previous president of the IAU Commission on Astrobiology, I visited many countries, and people everywhere are really excited about the possibility that maybe in the next 20, 30 years, we are going to find life. I mean, not as an ET or something, but simple microscopic organisms. So I think the chance is very real, in particular in view that we now know that complex organics are everywhere. Is quite possible that life could exist also elsewhere in the universe.
Yes, with all these exoplanets found in the last 20, 25 years as well, which we weren't sure about before, but now it seems maybe every star system has planets.
Yes, yes. Now detect signs of life in exoplanets are much more difficult because signals are very faint to do spectroscopic studies, but our nearby solar system objects probably, I mean, so like planetary satellites and so on would be probably the most likely place we detect signs of life.
Yes, of course. Well, at the beginning I mentioned that you had a book out recently, Our Place in the Universe, although it's volume 2 of a series, I understand, as in recently in the last 5 weeks or so, I think. Would you like to tell, as we are in a book fair, would you like to tell us a bit about your?
Yes, I'm very excited about these 2 books. I mean, I have 2 volumes, Our Place in the Universe. The first one talking about ancient discoveries. You know, our ancestors actually did know a lot about the universe. I mean, much more than most people realize. For example, they know how large is the moon, how far is the moon, and how large is the Earth. All these things seem quite incredible, but actually, our ancestors are extremely smart. And these developments of cosmological models and the change over our history have a lot of effect on society. And that's the theme of these 2 books are about. I mean, how development in science and in astronomy, in geology and in biology, how they affect our way of thinking and how it affect the social structure of human societies.
It sounds a very interesting approach with different parts of science and sort of anthropology combining as well, the study of society. It sounds very interesting.
Yeah, these 2 books also, I think, present a new way of teaching science. You know, the books are based on a common core course I developed and taught at the University of Hong Kong for all university students. And is different from the way how science subjects are taught. Usually we teach the substance or the content of the sciences, but I think it's much more important to talk about the process of science, how we think, how we change from one set of ideas to another. And this way of thinking is much more important and useful than just to a few scientists, because among my students, they were law students, they were social science students, they were humanities students, and they all benefited from learning how we learn and how we change our ideas over time. So I think this is the teaching the process of science is something that have not been emphasized enough in our science curriculum.
Yes, we keep all the science courses separate and don't integrate them as much as we could. I also want to ask you a little about planetary nebulae, because
yes, of course.
as you probably know, in Guadalajara we've had a few my very productive researchers in that, Peter Phillips and Gerardo Ramos, and you were about the morphologies, and because I have the understanding that you have some that are really are quite spherical or elliptical, and some that are more like a rotating disc with a bipolar structure, two jets coming out above and below. Would you like to talk a bit about the different forms?
No, I mean, I'm tremendously excited about research in planetary nebulae. I mean, myself, I've worked on the subject for several decades, and although we have made a lot of progress, we still haven't solved all the problems. And this morphology problem is one area that you mentioned, which is still very exciting. And in particular, now we have tremendous telescopes like the Hubble Space Telescope, which can take very detailed pictures of planetary nebulae. We have, for example, the ALMA array, which can detect molecular species inside planetary nebulae. We also have the SOFIA, a high-flying infrared telescope, which can detect the solid-state components in planetary nebulae. And they all together give us a lot more information than we can fully explain. And that's why it's such an exciting subject. Now, going back to your question of morphology, I mean, it has been known for 100 years that planetary nebulae have a variety of shapes. But the first question is that, are these shapes universal? Are they just different manifestations of a single structure? Now, if it is, then what are the physical processes that led to these kind of structures? And we know that now, I mean, planetary nebulae are formed by interacting winds, but the complication is that both the wind before, during the red giant stage, and the wind afterwards, during the pre-white dwarf stage, they both could be asymmetrical, and they can be time dependent. And these variables really complicates the understanding of the planetary nebula structure. And I want to emphasize that planetary nebulae have a lot of similarities to active galactic nuclei, except they are much better observed. We have much more data on planetary nebulae. So whatever theoretical progress we can make in terms of understanding the dynamics of planetary nebulae, I think can have wide implications on, for example, understanding structure of galaxies.
Again, and finally, I'd like to ask you about, as you mentioned, you did this undergraduate course in Hong Kong, and you were in Hong Kong for many years doing great things with a group studying planetary nebulae. And we had Quentin Parker on one of the roundtables earlier as well, working there. Would you like to say a bit about recent developments of astronomy in the Far East? Also?
Oh, yes. Now, of course, you know that the leaders of astronomy in the world, in terms of research, has always been North America and Europe and so on. And then in recent years, you are well aware that in Central and South America, there are also many groups emerging, doing very good research in astronomy. Now, in Asia, the first nation to develop was Japan, which definitely is a leader in many fields. But in recent couple of decades, other Asian countries are also moving forward, like China and also India and many Southeast Asian countries are also developing. Now, of course, the most important part is China. You know, China has extremely ambitious plans. They're building large ground-based telescopes. They are sending spacecraft to Mars, to the moon, and they are going to put a space station and with humans in there. You know, all these are very exciting for Asia. So I have been extremely grateful and glad that I have the opportunity to work in Taiwan and also to work in Hong Kong and have close contact with colleagues in China. And I'm extremely excited that Asia, and China in particular, are going to become important members of the world community in pushing astronomical research forward. And as you know, astronomy is a very old science, and it is a universal science. I mean, our universal urge to understanding the structure of the universe has history coming down from 3,000 years ago, and we are still pursuing because we are far from achieving a complete understanding of the evolution and structure of the universe. So I think it's very good that all countries are working together without consideration of national boundaries. Is a very good thing for humankind.
Exciting times ahead with more international collaboration, let's hope. Okay, thank you very much, Professor Sun Kwok. Thank you for your contribution to the book fair. And now I'll give the closing remarks and pass to effectively the next speaker.
Thank you very much.
Ok, gracias a Dr. Kwok por su contribución a la Feria Internacional del Libro. En unos minutos vamos a empezar con otra plática, otra invitada distinguida, doctora Jocelyn Bell Burnell de la Universidad de Oxford en Inglaterra, que va a hablar de la descubrimiento de pulsares, de lo que es más famoso por descubrir el primer pulsar durante su tesis doctoral en los 60s, pero ha sido muy productiva en recientes años, ha ganado muchos premios internacionales y vamos a preguntar a ella de esta también. Entonces va a ser muy buena plática y les invitamos a todos a las 7 en unos minutos. Ok, muchas gracias a todos.